present and at home. I'd like to welcome you to the 5th lecture by Professor Victor Pambuccian. And the topic of today's lecture is Into Dark Night, the Pasch axiom in ordered geometry. I would like to remind everybody that the 6th lecture is not next week, but it is tomorrow morning from 9 to 11. And that will lead us directly into the Easter holidays. So welcome to Professor Pambuccian, and the stage is yours.
Today's topic will be about the Pasch axiom. We all know that there was a lot of work on the parallel postulate, which was considered mysterious for a long time. It has lost much of its mystery in the meantime. But there is another axiom that appeared rather late in the history of mathematics in 1882, which is this Pasch axiom. That is still very much mysterious, and I'd like to travel the path of its mysteries and what we know and we don't know about it. And I find it rather remarkable that a statement about a very fundamental thing, order in a plane, what is left and what is right, turns out to be actually the most complicated thing, and that the complications were ignored for the better part of the 20th century, and they were left to me an insignificant quantity in the foundations of geometry and in mathematics altogether, to have something to say about it, which is unusual, because I thought that the important things that were said in logic and in all these things were mostly said during the first half of the 20th century, and that for later times only minute details and very complicated things were left. But this is a very fundamental thing, and I was very surprised that it was left in that stage. So we'll see what it is all about and what the problems are. So it was introduced by Pasch. Gauss had noted sometime that there is some need for, order axioms, but otherwise nobody did anything between Euclid and 1882 to express this idea that, for example, the 5th axiom speaks about on the same side of the two lines that meet are on the same side of this line that intersect. Well, what does that mean? All of the elements is full of looking on one side rather than the other. And Pasch expressed this in terms of points and segments. So a point is on a segment. And this you can equivalently phrase in terms of betweenness, a ternary predicate that when you say let's say Z of A, B, C, then you say that B is between A and C. Why Z? Well, there are two types of betweennesses. One is Tarski's B, where you allow the middle point to be equal to the end point. And the Z, which is the strict betweenness. Why Z? From zwischen, because it appeared in Hilbert's Grundlagen der Geometrie. It wasn't formally expressed, so I kind of gave it this name to distinguish it from Tarski's betweenness. So what do you need to express order with this? Well, there are two things you need. The one is you need to say, what does it mean that a point divides a line into two half lines? And that's easy. There is no mystery regarding this. There are a bunch of axioms that do it. Well, first of all, you have to say that this relation is symmetric, that it doesn't matter whether B is between A and C or C and A. The second is that once you figured out which way 3 points are in between us, any other way won't be true. The next one is one of these 4-point axioms that tell you that if C is between A and B and D is past B, it's like here, so this is A, B, AC, B, D. So if you have something like this, where you know that this is between these two, and you know that this is between these two, then you can infer that this is this way. And there are several like this, 4-point axioms. And that's it for universal things that you can say about it, all linear. And then you want to say that this is unending. And you also want to say that it is dense. Unending means there is no end of the world, you know, there's always something past something. And dense means that every interval contains something in between. So that's it. That's all you can say about order on a line. If you add to these axioms an axiom saying that any 3 points are in some order, then you get linear order on a line which is dense and without first and last element. This theory was shown in 27 by Langford to be decidable. So it is as uninteresting as it can get. There's no mystery about it. The dependence and independence of those axioms has been studied intensely by the so-called American postulate theorists. So we know everything about it. So one-dimensional life is beautiful, easy. Now, for our later discussion, let us introduce two defined relations. One is lambda and the other is L. Lambda says that 3 distinct points are on a line. Okay? And L says that A, B, C are 3 collinear points, and they could be also equal among themselves. Okay. Now, this peaceful situation changes dramatically when you want to go to the 2-dimensional realm. Well, what would you want to do there? Well, you have a line in a plane, and you want to repeat the story that you did in the one-dimensional case. In the one-dimensional case, all those axioms that you've seen before were meant to tell you what it means for this point to divide a line into 2 half lines. If you go 1 dimension higher and the line is replaced by the plane and the point by the line, then you have the same problem. This line divides this plane into 2 things, 2 half planes. How do you do that? How do you express that, it does that? And that's where the Pasch axiom enters the picture. Now, what do you want of these half planes? You want the same thing that you wanted from the half lines, actually. You want 3 conditions. You want that if A and B are in different half planes, and A and C are in the same half plane, so think about the line like this. A and B are indifferent, but A and C are in the same. Then you expect that B and C are in different half planes. That's a simple thing, it's intuitive. Now, if A and B are in different half planes, and A, so this is A and B, and A and C are also in different half-planes, then B and C should be in the same half-plane. That's again very easily seen. Now, if A and B are in the same half-plane, and so is A and C, then B and C should also be in the same half-plane. These are the three things that you can think about when you think, like, what do I want half-planes to do? That's what you want them to do. Okay, well, the question is, how do you express being in different half-planes? And Pasch's idea was to have a witness for this happening. And the most immediate thing you can witness it is to say that, suppose this line is a river, and the 2 points are 2 houses on, in the landscape. How do I know whether the 2 houses are in the same, on the same riverbank or on different riverbanks? Well, the question is, if I look from my window to the other house, do I see the river or not? That's what Pasch used as being in different half-planes. So you say there is a point on this line that is between these 2 points that are supposedly on different half-planes. And if there's none, then you say they're on the same. Now, from the 3 conditions, 1 to 3, listed earlier, you need only 1 to be taken as an axiom. 3 itself is a variant of 1, and 2 is derivable. So let's see who 1 was. So you need to say only this, that if A and B are in different half-planes, and A and C are in the same half-plane, then B and C are in different half-planes. Well, this is exactly the Pasch axiom, because what does this A and B in different half-planes mean? It means that a line, this line, has entered the triangle ABC. The other part says it can't exit it in AC, right? Because AC are on the same side, right? So if it can't exit it here, then it ought to exit it somewhere. Right? So a line that enters a triangle exits it somewhere. Yeah. So a line G that is not incident with any of the vertices of a triangle and intersects one side of a triangle must intersect another side as well. Notice the axiom does not specify an either or. It doesn't say it intersects one and only one of the sides. The reason is that it can be proved that a line cannot intersect all 3 sides. Yeah? This is called Pasch's theorem. I mean, I call it. I haven't noticed it in the literature, but I gave it a name. Because Pasch actually proves that. And this is what 2 said. So since you can prove Pasch's theorem from Pasch's axiom, you don't need to speak of 2 anymore. What was 2? 2 was that A and B were in different half-planes. A and B. And A and C were also in different half-planes. Then it says that B and C must be in the same. In other words, this line, we're told, intersects 2 sides, AB and AC. Then it can't intersect BC as well, is what 2 says. Well, that's Pasch's theorem. You don't need to take it as an axiom because you have it. You would want to also add a lower dimension axiom, something that tells you that there are at least 3 non-collinear points, because else you could have models that are all linear, and well, you don't want that in general. You want to have some richness in your. theory. Let L denote the theory of the linear axioms, so those that exclude before the Pasch axiom, together with the lower dimension axiom. So this will be the ambient theory that the discussion will be happening in. Now, the Pasch axiom is a specifically two-dimensional axiom. Why? Well, look, it says that if you have a triangle and somebody enters it, it must exit it. But if you are in higher dimensions, you can, if you have here a triangle, you can enter it this way and you don't exit it anywhere. So the axiom itself forces two-dimensionality of the world. Peano, in 1889, in I principi di geometria logicamente esposti, was asking for a generalization of this Paschen world in which you can go in arbitrary dimensions, arbitrary unspecified dimensions. And there he found that you can't say the Pasch axiom anymore in that way, but you can say it in two different ways that are axioms 13 and 14. But since in Schwabhäuser, Schmierle, Ptavsky, these are called the inner and outer form of the Pasch axiom, I will stay with them that way rather than saying that they are axioms 13 and 14 of Peano. So what does the inner Pasch tell us? Well, if you look at the picture, you have the triangle ABC, and you have a line, DC, that does two things. It has a point in common with a line with a side AC, and a point in common with the extension of the side AB. Then you're told that CD, the segment CD, intersects the segment CB. Okay, so what does it, why is it a Pasch type axiom? Because it says, first of all, this line CD entered the triangle. We know it cannot exit it on the segment AB because we know it already intersects AB on the outside. Pasch told us that a line that enters it must exit it. Well, this exits it. It exits the only other side it could. It tells you a little bit more because it says that F is not just between B and C, but also tells you that it's between C and D. Okay? You could also look at the whole story as a story about the line CB and the secant CB and the triangle ACD, because it's completely symmetric, right? It's also sometimes called the scissors theorem because these two lines that intersect here look like a scissor. You know? That's inner Pasch. Outer Pasch speaks about, again, a triangle ABC, a line CD. C is on the side BC of our triangle, and D is on the extension of AB. Right? So now we have the situation similar to here, but the extension of the side our line intersects is adjacent to this one. Here, it was on the other side, right? So it's a little bit of a difference. And the difference, the more important difference, is that the intersection point is now on the extension of this side rather than between them. Yeah. So you got this, the side CD intersects the side AC in the point F. I mean, the line. And the original statement says that C is between F and D. Veblen showed in 1904 that you can drop this requirement. if you just say that the line itself intersects AC as a segment, then you can prove that this is in the right place. Okay? So these are the two versions of Pasch that were introduced by Peano for higher dimensional purposes. Veblen proved that out of outer Pasch, you can get inner Pasch. Okay? He even stated that the converse is true, that you can get outer Pasch out of inner Pasch. Coxeter, in his introduction to geometry, was of the opinion that outer Pasch is independent of inner Pasch. But the only justification he offers is that if we try to use IP as an axiom, we would not be able to deduce OP as a theorem. That's all. Well, which way is it right? Well, it turns out that actually the inner Pasch does not imply the outer Pasch, the way Coxeter said. There is as yet no model for this. The proof that I presented in 2010 is proof theoretic. So what would a geometry look like that just satisfies inner Pasch but not outer Pasch? We don't have that. Okay. Yeah, this tells you what the proof theoretical details are. Now, since we found out that the inner Pasch is weaker than the outer Pasch, we might be interested in a stepwise construction of things. So this means that inner Pasch, you want to go through inner Pasch, and you want to add something to get to outer Pasch. Now, you don't want to add something ridiculous like, inner Pasch implies outer Pasch. You want to add something geometrically meaningful. Those things I call missing links. And here is what a missing link should be doing. So a missing link from inner Pasch to outer Pasch should be something that outer Pasch is equivalent to the conjunction between inner Pasch and the missing link. The missing link itself is weaker than OP. And the ambient theory does not imply that one of IP or the missing link is true. The last condition is there to disallow IP implies OP as a missing link. The missing link turns out to be weak Pasch. I proved this in the same paper. It turned out that Martin Schröder from had done the same thing, but I had seen this after I submitted the paper. It was in his Nachlass at the University of Essen. So, what is weak Pasch? Weak Pasch has the same hypothesis as outer Pasch, but asks only that the two lines intersect. What does that mean? Here it is. So you have the same hypothesis that you see here in outer Pasch, but you're asking only for the line here and this line to intersect. You're no longer stating that the point of intersection F is between A and C. You say anywhere here, between here or between here or between here, and on the other side again, you're not specifying where it lies. This was first considered by Van der Schmielev in 1980. And that turns out to be precisely the missing link that we were looking for. Now, you could ask yourself, what would happen if we were to add the fact that there exists a unique parallel from any point to any line? So if we were in affine geometry, could you then using IP, prove OP, it's not known. Martin Schroeder claimed that this is true, but there is no proof. So the problem is open at the present. Okay. What is the missing link between the outer Pasch and the Pasch axiom? Right? Because we know, okay, outer Pasch is something that's true in any dimension, right? Pasch is specifically two-dimensional. So it's absolutely clear that OP is weaker than P because OP is true, for example, in three-dimensional space. So what's the missing link there? There are several such, and I mentioned only two that I found rather interesting. The planarity of K5 and K33. So what are these? K5 is the complete graph on 5 points. So take 5 points and join each with each. Okay? Saying that it's not planar means that no matter how you put 5 points, two of the segments that you join between them must intersect. And what does K33 say? It's the so-called utility problem. Imagine you have 3 houses and you have 3 utilities. Electricity, gas, and water. Can you make it so that, I mean, the utilities come from different places. There's a electricity place, a water place, and a gas place. And can you have these connect to the 3 houses without any of them intersecting? And turns out that no, that's not the case. You can't do that. So saying this, these are statements of ordered geometry. If you think that the joining have to be lines, it can be easily shown, not easily, but it can be shown that if there are any joinings, topological joinings, then it's possible to do them with lines as well. And these are important because there are some old topology theorems that say that a graph is non-planar just because of these 2 people. It must contain something, one of these 2 in it. That's the culprit of non-planarity. So what if we want to go from inner Pasch all the way to Pasch? So this was from outer Pasch to Pasch. What about from inner Pasch to Pasch? Well, then we need to add this axiom L, which says that if you have 4 points, A, B, X, Y, then the following happen. Either X and Y are on different sides of AB, like in the first picture, or else that X, Y, if you make the triangle, AX is not on the line AB, right? And if Y is inside the triangle ABX, which means this happens. Yeah? So you have the extension of XY intersects AB. Or else it's the same thing with X and Y interchanged. So X is inside the triangle ABY, or else ABXY form a convex quadrilateral. And then the segment BX and AY intersect, or AX and BY. This is a flipping of that. That's what the axiom says, that no matter what 4 points you have, one of these things occur. So if you got this, and you add it to IP, then you get your Pasch axiom. Yeah.
What's the relationship between L and this Pasch plus, like, let's say, one of the conditions K5 or K3?
weak Pasch and yeah.
Because I mean, if you add weak Pasch to
Yeah.
P, you would obtain OP, and then add the other conditional.
Yeah, weak Pasch, we said IP and weak Pasch gives you OP.
Yeah, exactly.
Okay, so
if you add the conditions, you obtain P.
yeah, if you add both weak Pasch and L, but that's too much, right? So you ask something else.
No, not if you add in L. If you add weak Pasch plus the conditions you already studied for OP. Like K5 or K5.
These people. No, they wouldn't work. Because, so, weak Pasch doesn't give you enough of, you mean without IP, right, or what? With IP, yeah, but that's too much already, isn't it?
Because I wonder whether you could prove that, like you could prove further conditions based on the fact that you would want to obtain.
Yeah, I understand what you're saying. So if I add to IP the non-planarity of one of those graphs, and in addition to it weak Pasch, then I should be able to get P. Yes, I think so. Yeah, that's plenty. Yes.
Yeah, I wonder if you could prove maybe a stronger link or L as a mandatory condition, or like.
Here it's an art, I mean, because the missing link isn't, I mean, the logical definition that we have of a missing link does not specify the fact that it should look and feel like an axiom, which is an aesthetic element of it. So, yeah, there are several. I'm not saying when you think the missing link, it seems like it's a unique object. It's certainly not. Certainly. Now, Pasch's theorem, we spoke about it already. And so the fact that a line cannot intersect all three sides of a triangle. Now, it is known that you can use just OP to prove PT, right? Pasch proved it from his Pasch axiom, but OP is good enough. IP is good enough, in fact. And so you can ask yourself now, what if I want to start with OP, with PT, and build up, what would be the missing link between those things? And the strong weak Pasch does the job. What does the strong weak Pasch say? Well, weak Pasch just said that those two lines that appear in outer Pasch intersect at all. This says that the point F is allowed just these two things, the point F, so AFC or ACF, just keep that in mind. Here it is. So AFC, so it's either inside or ACF. So it excludes it being on this side, right? It still allows just the line CD to intersect, yeah? So the position of F on the line CD is arbitrary, could be anywhere, but it's not allowed to be on the extension here. That's why I say strong weak Pasch. It's still a weak Pasch, but stronger. Yeah. So that's the missing link. So if you take Pasch's theorem and you take strong weak Pasch, then you get OP. And that answers already your question, doesn't it? It more than answers it, because you are asking, if I start with OP and add weak Pasch and one of the non-planarities, do I get what I want? And I get it already with a strong weak Pasch. So all you need to show is that you can get the strong out of the planarities, the non-planarities. So We don't know if it is weaker, if strong weak Pasch is weaker under L than outer Pasch. But if it is, then it's the missing link. What's the missing link if you want to go from Pasch's theorem to full Pasch? It's the weak crossbar theorem. Now, what's the crossbar theorem? The crossbar theorem says this. If you have an angle, let me draw this with the, how did we get this here? Let's make it come up. Okay, not that. And here,
you already have the drawing. That's drawing.
yeah, I just take this. Now it's going to be fine. So, crossbar theorem says this. If you have a point P inside this angle, and you have here a segment, then this intersects that. So, this point here is known to be inside the angle. How do you say inside the angle in general? The angle is in general given by A1, A2, A3. And the way to say that a point, say, well, A4 is in the story, lies inside the angle is to say that A4 and A2 are on the same side of A1, A3. And A4 and A3 are on the same side of A1, A2. Because if you think of the side here, that's that, right? And if you think the other side is this. So the intersection of those is just the inside of that angle, yeah? And so if you know that A4 is inside the angle, then the ray A1, A4 should be intersecting this. That's the classical crossbar theorem. It can be proved with Pasch's theorem. Now this one says something else. That's why it's weak. Because it says that A4 lies inside the triangle A1, A2, A3. So it doesn't allow it to be on the extension, as it were. Huh? Then it must intersect. Now it doesn't want me to do that because I need to get rid of this, which I do by picking this. Just kill this and then it forgets it. That would be nice. Not quite. I need to do this first and then, yeah. Now it forgot about it. Okay, good. This is the formal statement. This is why I gave you a picture, because you probably won't like the formal statement very much. If the weak crossbar theorem is weaker than the Pasch axiom, which we don't know, then the weak crossbar theorem is actually a missing link between PT and P. This has a significant importance, even if it's not weaker or whatever. Why? My search into this ordered geometry was connected with asking myself the following question. Is this Paschan axiomatics the simplest possible? Now, what is simplest? There are many ways to put it. So I was thinking simplest in purely syntactic terms. And in purely syntactic terms, one measure of simplicity is to see what is the greatest number of variables that you need in the axis. You've seen the linear axioms. They were doing fine with 4 points. And it's clear that you can't get anything interesting with just 3. You need the 4th to do something. The Pasch axiom, though, is a story about 6 points. No matter whether you take it in the original form or in the inner, outer, or whatever, it's 6 points no matter what. It has 5 points that are universally quantified, namely vertices of the triangle, the place where this line enters the one side, and the line has to be determined by 2 points. So there needs to be another point as well. That's the 5th point. And it says that there exists a 6th point. Okay? So my question, to which I'll come back, is if you could do it with just 5. And that is still unknown, oddly enough. Something as simple as that. But the next question is, having this exists in Pasch's axiom depends on 5 earlier variables. So if you think in terms of Sculemization, it's a function with 5 arguments. Having one with fewer makes it simpler. And that's what our splitting is. So we've shown that you can split P into weak crossbar theorem and Pasch's theorem. Pasch's theorem is a universal statement about 6 points. It just says that if you have a point on this side and this side and this side, that these 3 points cannot be collinear. There's no existential anywhere. And the weak crossbar theorem, as you see, it starts with 4 points and gives you a 5th. So it's the Sculem function is one about 4 variables. Okay. Now, the deeper question is, do we need any statement with 6 points? I mean, in this form, if we could show that the weak crossbar theorem is equivalent to the Pasch axiom, then we'd be done. Because it's a 5-point statement. It is easy to show that you can't do it with 4. That's simple, right? So you can show that there cannot be any axiomatization of ordered geometry, be it 2-dimensional or higher dimensional with just 4 points. We know we can do it with 6. The question is, what's the state at 5? So I looked at all the possible statements that you can make with 5 points. And here I'm going to draw again something. Drawing here. And this. So first of all, you're saying, okay, I have just 5 variables at my disposal. There's no point with starting with an existential quantifier. Why? There's no preferred point in the universe. So anything that's true with an existential in front will be true with a universal. The second one shouldn't be existential either. Why? There's no special point after you've chosen the first one. So start with 2 universals. Great. What about the third one? Again, there's nothing special. If you have 2 points, there's no special point that is the third point. All you can say is it lies on this line or not. That you can say universal. What about the fourth one? Even for 3 points, there's no special fourth point that is, you have a triangle or 3 points on a line. There's nothing really special about that fourth point. So you should start with 4 universally quantified variables. Great. So what can be, this is blocked now, so I have to draw here. Okay. So I start with this. So I have for all ABC, let's say. And I will say what? I will say either ABC are collinear, in which case I don't care. Or else, now I have a fourth point. Or else, what can I say now about this fourth point? All I can say is either the fourth point lies on the existing lines already, in which case, again, it's not interesting. So these are disjunctions, right? You would say that either this or this or this. Or else, what happens if it doesn't lie on this? Well, then it lies in one of the regions determined by this. This is the first one, second, third, fourth, fifth, sixth, seventh. There are 7 regions where it could be. How do I know in which one it is? Well, that's where the existential quantifier will come into the picture. If it's inside, there are 3 ways of witnessing its insideness. Namely, you would say if this point, you know, A, B, C, D, let's say, is here, then you would say there is a U that is between B and C, so that D is between A and U. You could do the same thing coming from B. You could do the same thing coming from C. So there are 3 ways to say that the point is inside. What about these things? Here is the, let's see, the Roma. Okay. And now let's go back to this. Okay, now, what about if you're here? There's only one way to say that you're here, not 3. Namely, you will say this. There is, if your D is here, then the U will be here, and it's between A and C, and U is between B and D. So these areas have just one way of witnessing the fact that the point is there. What about the, let's do again an erasing of this, okay. Oh, the C was pretty good, yeah. Okay, so let's put the C back where it was. And now, what if you're here? D is here. Then there are again 3 ways of saying it. One is this. There's a U here so that things are like in the picture. Or you could say it this way. There is a U here so that things are like in the picture. And the third one is this. Okay? Exactly, yeah.
No, because I'm confused, because the first way you're saying it, couldn't the point also be in a region under BC?
Let's see. So you're saying which version could be somewhere else?
No, I mean, if you're saying that the segment AD
Yes.
touches.
No, not the segment. I'm saying that there is a U that is between B and C, and such that DAU, that A is between D and U.
Okay, so A must be.
Yeah, I'm saying so that things are like in the picture. So look at the picture and write your Z's the way you see the picture. Yeah. Okay, so we got then 4 areas, 1, 2, 3, and the inside, where you can say the fact that the point D resides there, you can say it in each of them in 3 ways. The others are uniquely in 1 way. So what you will say is that D is either here or here or here or here or here or here or here. And in those that you have multiple ones, you can switch which way you're saying this. So since you have 3 here, 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 and here, and there are 4 such, you have 3 to the 4 ways of saying it. You have 81 ways of expressing this. You have 81 different axioms with 5 variables. No, not this, rather this. Okay, and now we want to kill this and hope for the best. Yeah. But in these 81 statements that I was talking about, there are certain symmetries, right, which you expect. Removing those symmetries, you're left with 15 statements. Okay? One of them, a little bit stronger than will be the weak crossbar theorem. It's going to be a little stronger. Now the question is the conjunction of all these 15 statements strong enough to prove P? Well, this is unknown. So we don't know whether ordered geometry can be expressed with 5 variables or not. You can now move on to another area, asking whether there isn't a more liberal or more generous way of defining separation. We know that in Pasch, separation required a certain continuity of a segment or of the line, right? But imagine your river has some dry patches, and you look at the other house on the other side and you don't see the river at all. But that doesn't mean you're not on different sides. Well, this tries to alleviate that. And you're saying, if I have 2 points, A and B, then you decree that they are on the same side of this line determined by U and B. If there is a P, there exists a P, such that, and there is an X and a Y, such that X is between A and P and Y is between P and B. So all you need is to know that there is a place on the other side of the river where from there to A and from there to B, you can see it. So this is in formal language. Now, what the first axiom says is that if the points A1, A2, A3 are not on the line determined by U and B, and A1 and A2 are on the same side, and A2 and A3 are on the same side, then A1 and A3 are on the same side. So this is our old condition 3. The next one says that if A and B are not on the line UV, and they are on the same side of UV, and C is a point between them, then A and C is on the same side of UV. This is a kind of convexity of half planes, right? If you have 2 points in the same half plane and a point between them, so the whole segment is basically in the same half plane. That's what it says. And that's, I explain what they say. And you have one more axiom that says that A and B, how do you define now? We just defined that A and B are on the same side. How do you now know whether A and B are on different sides? And this is the story. They're on different sides if there is a P, an X, and a Y that are just like in the picture. So again, it's a roundabout way. Remember, in Pasch, it was just that you join A and B and you see if there is something in between. This is much more generous because it allows for the existence of any point here so that these two give you this story here. Yeah? So adding to L these things and inner Pasch, you get the Pasch axiom. So this is an alternative axiom system for plane ordered geometry. It is not known whether these 3 are needed. All. Can you do it with fewer? Nobody knows. Now, let's move on to, so far, we're done with the analysis of just pure betweenness geometry. We know that betweenness occurs in Euclid, but Euclid has congruence as well. So how is the situation there? Well, let's look at Tarski's axiom system. In Tarski's axiom system, there are some universal axioms. And then there is a segment transport axiom that is existential because it says that this segment can be transported on some rate. And it has the Pasch axiom, which is also an existential one. And the parallel postulate through the form that from any point inside an angle, there is a line that intersects both sides of the angle. To these, it has a first order continuity axiom. So Cantor Dedekind, where the two sets that define the Cantor Dedekind cut are defined by first order formulas. So they're not any sets because you don't have set variables. So it will be an axiom schema. So for every first order formula, you have a different axiom. Is the Pasch axiom independent in that axiom system? This is unknown. The reason it is unknown is that the parallel postulate is also in this betweenness form. And that complicates things tremendously. However, P is independent if you replace that parallel postulate with one that says nothing about betweenness, which is a pure congruence axiom. It says that for any 3 points that are not collinear, which you can express also in terms of congruence, there is a center of the circumscribed circle. So in other words, there is a point that is equidistant from all three. So you can add to these everything that is universally true about order and congruence. You can add the axiom that says that every segment has a midpoint, and you can add segment transport to it. And you can add the second order continuity axiom. So the usual Cantor Dedekind with sets. And it's still independent. This was shown by Szczerba in 1970. And it was achieved by using non-continuous solutions of the Cauchy functional equation, which is the one you're saying there. Such non-continuous solutions depend on the axiom of choice. Any such non-continuous solution will also give you a non-measurable set. Adler showed in 1973 that if you assume the axiom of determinateness, then you can no longer get models of independence for the Pasch axiom. The Pasch axiom actually holds in all those. What is the axiom of determinateness? Perhaps that's not as simple. Suppose you have a subset of 2 pre omega. What is that? That's the set of functions from omega, which is the natural numbers, to 2, which is the set consisting of just 0 and 1. So you can imagine these as sequences of zeros and ones. There's a game, depending on who P is, which has 2 players. One chooses some element in 0, 1, then 2 chooses another element in 0, 1, then 1 goes on and chooses another one. And by the time all time is over, they have ended up with a sequence. The question is the sequence in this set P or not? If it is, then player 1 wins. Otherwise, player 2 wins. The axiom of determinateness says that for every subset of 2 pre omega, one of the players has a winning strategy. We know that if this were true, then the axiom of choice is false, which is rather hard on God, because if you're God, you would think that you certainly know this, and you certainly know the axiom of choice, but you can't know both. So It's not known, though, to be consistent, although everybody believes it is. So it's not known that Zermelo-Fraenkel with AD is consistent. Should Zermelo-Fraenkel be consistent to start with? Now, what is the degree of incompleteness of the Pasch X? So let's call Pasch-free geometry the stuff that I said before. I mean, throw in everything universal about congruence and betweenness. Throw in the existence of a midpoint, the segment congruence axiom, and the first order continuity axiom. Call this Pasch-free geometry. There are 2 to the Aleph 0 many complete extensions of Pasch-free geometry, as shown by Szczerba in 71. But we don't know if any of those extensions is a finite one. So the one when you add just one axiom. In other words, put it this way. If you do the same story and you remove the parallel postulate, right, and you leave everything else in Tosca's axiom system intact, then there are just 2 extensions, Euclidean and hyperbolic. Here, you have continuum many. And we don't know if there is a really non-Paaschian geometry in which you just replace Pasch with something else and get it to be complete. Because in the case of the parallel postulate, both are complete, both Euclidean and hyperbolic. Here it may be that these completions are all very bad. They may be even non-recursively axiomatized. Now here is a historic mystery, an aside, that I could not solve, is regarding Gabriel Sutton, who was a professor at the Polytechnic University of Bucharest from 41 to 66, and who wrote in his short autobiography, which you had to write for becoming, full professor and those kinds of things. He wrote that he proved the independence of the Pasch axiom using the well-orderability of the continuum, which is well known to be equivalent to the axiom of choice. He was of Swiss Romand origin, which is rather rare in Romania and rather rare to stay during the time he stayed there. And I couldn't find any publication where this is proved, nor any paper in his Nautilus for that matter. This cannot be incorrect, though, because he was a person of extreme modesty. For example, in the 1970s, some researchers in recursiveness in Romania found out that actually he gave the first example of a recursive, non-primitive recursive function a year before Akka. And so they made a big fuss about it. They organized a conference and so on, and he refused to even show up. He got his PhD in 1925 with Hilbert. I haven't looked at his thesis, although the subject has nothing to do with geometry. It may be in some footnote that of something, or I have no idea, or he just showed it to in a conference and thought it's not worth publishing. I have no idea. I wrote a paper in the 1980s, at the time when I was considered a parasite in Romania, because I had no job. And there used to be a section of the American Mathematical Monthly that was called Progress Reports. And it contained things that were done in the past 15 years that were of importance and the general public should be interested in. So I wrote something about the proof of independence of Pasch, and I mentioned Sudan and so on. And I wrote that the latecomers, which I considered Sudan to be a latecomer because he hadn't published anything, were in both cases from Romania, but both of them were not Romanians. The one being János Bolya, which was Hungarian, and the second one being Gabriel Sudan, which was Swiss. I've sent it, waited, and nothing happened. And I've sent it again and waited, and nothing happened. And then I realized, oh, I should remove the statements about them, not being Romanian and so on. And then it arrived, but the rubric had disappeared in the meantime. It was no longer there, which meant that the secret police read even things that you sent to a mathematical journal very carefully and kept them away because this was something very bad to say in Romania at the time, because obviously there were no non-Romanians and so on. So what happens if you put the circle axiom in? Remember, the Pasch axiom is a continuity statement of sorts, right? It says that if you're there and there, then this, basically, if you want to go from a country to another one, you have to cross the border. But the border is a line. What about if the border is a circle, right? You have a circle and you want to go from this country to that country, The circle axiom says you have to cross the border. So you have to cross kind of a second degree border, if you think of it right. The other one says you have to, cross a linear border. So Vanda Shmelev showed that if you add the Pasch-free geometry without the elementary continuity axiom, the circle axiom, then you get the Pasch axiom. This she did by creating a coordinate system and showing that the field that you get there is Euclidean order, and thus that it's ordered, so you're done. But there is no synthetic proof now. So we don't know how to actually deduce Pasch from circle axiom, but I think it's an important thing here. Gupta and Prestel in 72 showed that the triangle inequality, or equivalently the statement that the hypotenuse is longer than the side, is strictly weaker than the Pasch axiom. And here I was thinking of the missing link. And in 1996, I could find that this is the missing link. What's that? Well, you have a triangle OAC, which is right. You have a right triangle. You have an arbitrary point B strictly between O and C. You drop a perpendicular from B to AC. Then it says that this thing, BD, is smaller than this thing. Oddly enough, I could show that this, together with the statement that the hypotenuse in any right triangle is greater than the side, these together give you the Pasch axiom. But I don't know whether you need, this is clearly needed, because as shown previously, if you just have that the hypotenuse is longer than the side, that's weaker than the Pasch axiom. But what's not known is whether you need this, whether you need the first part, the hypothesis is longer than the side. Because here, if you think about it, if B were to be O, then this says precisely that the side is less than the, so in the limit, this statement becomes the other one. But this is for strictly between. So do you need both? It's not known. Now, with this, this is the last part of the talk, is why Euclid did not need Pasch. And this is a paper I'm in the process of writing now. So Euclid, as we mentioned in the first talk, expresses it by saying that if a straight line falling on two lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. And I claim that we can prove the Pasch axiom if we have this. So, first of all, this clearly involves a heavy amount of what? Of order. Because first of all, you need to know it sees meet on the side and so on. So you need to know what the side is, right? You need to know what it means that the angles that you're talking about are on the same side. And you need to know how to add angles. That's also not easy if you don't know what order is. So you need a lot of stuff here. So how can we, so to say that I prove Pasch out of it, it means that I don't assume it. And here is how you cannot assume it. This was done by Sperner in the 1940s. It's called semi-ordered geometry. And the way you do it is with points and lines, and point is incident on line, and a ternary relation that says that 2 points are on different sides of the line G. The axioms that you need are these. If 2 points are different and there is a line, they lie. The line is unique. The joining line, if the 2 points are different, is unique. And now comes this. There are 3 points that are not on any line, so it's at least two-dimensional. If A and B are on different sides of G, then A is not on G. So the D thing occurs only about points that are not on the line. If A and B are on different sides of G, then so are B and A. If G is between A and C and B and does not go through C, then it must go through AC or BC. This looks like the Pasch axiom, right? The only difference is it's not the Pasch axiom. Why? Because the Pasch axiom speaks of really between things. Here, there's no betweenness notion. We're just saying you're on different sides or something like this, but we're not saying that we know that you're on different sides by means of the betweenness relation. Okay? This one says that this is the so-called Pasch theorem. It says that a line G cannot go through all 3 sides of a triangle. It doesn't even say that it's a triangle, because if they're on a line, then it's even more so. No? So the last one is the so-called Gerade relation that says that okay. So this one says this. If I have A, B, C, and I have C is here. Let's use this. Boom, boom. This. It doesn't want to. What did I do wrong?
You just have to click on it. Just quick accessible.
Okay. Oh, I started it somewhere else.
Yeah, you can also drag it. Click and drag it.
Okay, good. So this is an unusual case. Yeah. Okay, good. So I am putting here C and here B. And it says that if I have two lines going through C, H and K, then if A and B are on different sides of H, then A and B are also on different sides of K. So in other words, it doesn't matter which line I pick here, provided obviously it's not the line on which these lie, because then it makes no sense. But for all those lines, if A and B are this, then if are on different sides of one, they're on different sides of the other. Now let's get rid of these and come back to this and this. Now, you need to add to these lots and lots of axioms, things that allow you to compare angles, things that allow you to add angles. But if you throw in all that, then you can actually prove the Pasch from the parallel postulate. This was mentioned in a short note by Salvatore Di Noi in the Bollettino dell'Unione Matematica Italiana in 1949. It was a historical note. He provided no justification for it, but that's that. And this is the end of my talk today.
Okay, so any questions in the audience or at home?
Yes,
Yeah, on you go.
verification. So if we take the dusty axiom system,
Yes.
and we remove the Pasch axiom,
Yes.
we can prove it from there.
It's not known.
It's not known, okay, because the Euclidean axiom is not the original one, it's just about.
Yes, because the Euclidean axiom of Tarski is this pure betweenness statement. And why Szczerba's model does not work is because Szczerba actually does this. He takes a Cartesian plane over the real numbers and leaves congruence intact. Namely, you can think about it as everything in a Cartesian plane can be expressed in terms of this norm. And the norm is usually defined as the norm of x is of a point, say A, of coordinates x and y, is defined as the square root of x squared plus y squared. But we know that there are two square roots to everything. So you choose always the positive one. Okay. Well, what Szczerba does is he creates a positive cone in which usually what is a positive cone? So you have an ordered field. Or you have a field, let's say. The way you can define order is to say that an element is greater than 0 if it belongs to a positive cone. Now, what is a positive cone? Well, a positive cone is something that needs to satisfy three things. The first one is that P union with no negative P is the whole, with 0 is the whole field. The second one says that P intersects negative P is empty. And then you're saying P plus P is included in P. So the sum of two positives is a positive. And the third one says that the product of two positives is a positive. So P times P is included. What Szczerba does is he, and usually you say also that 1 is in P, that 1 is positive. Okay, what Szczerba does is says, let's remove the multiplication condition. So you no longer know that the product of two positives is positive. To create such half orders or semi orders, whatever, is he does it by, if you want to do it on the real numbers, then you need some, the non-continuous solutions to the Cauchy functional equation. And what you can control very well in these models are statements about segment congruence, because they stay the same. It doesn't matter. Because in the segment congruence, you can say what? The square root of something is equal to the square root. Okay, but the square root is the positive thing. Yeah, but this is true if and only if the squared things are true. And in the squared things, there is no positive. So everything about, so it doesn't do anything to congruence, to the usual congruence. It messes between us badly. Yeah, so everything that, so because Szczerba chose this form of the parallel postulate that is purely congruence, it does well. But in Tarski's axiom system, it is purely between us. And you have no control over whether this is true or not, or creating in, creating, because after Szczerba, people have constructed such orders, such semi-quasi-orders, whatever I forgot what they're called. Semi-orders, perhaps. I mean, they have nothing to do with Sperner's semi, so that's why I'm trying not to say that. So they have tried to create these in other fields, and say just Pythagorean ordered fields that have nothing to do with the reals. So you have many such orders, but to control what's happening, whether there is this line that intersects those, it's impossible, because none of them are constructive enough so you could say this is or isn't. So it's hard to get it to be true while Pasch is not true. So I don't know whether I have an opinion on the matter, if you can do it with it or not. I think that I mean, if I think proof theoretically, I see no way to prove Pasch by using that form. Why? What does that form say? It says that if you have a point inside of an angle, then there exists a line. That's very weak. That gives me just two intersection points that exist. Pasch asks for all there should be this. So I can't get this for all out of these few that may exist. So if you could formalize that, then you have a proof theoretical proof that you can't do it. So I don't think that it's dependent in that axiom, just saying there is no independence model. Yeah.
Questions? Yeah, go.
Just one clarification. At a certain point, you said that AD, I believe, is incompatible with the axiom of choice.
Correct.
Yes, can you elaborate a bit on that? Or at least I have not understood it really well.
So,
in what sense?
if so, in ZF plus AD, you could prove the negation of the axiom of choice.
Okay.
And vice versa.
Okay.
So in ZF plus AC, AD is not true.
Okay.
Yeah? So they're exclusive of each other.
Other questions at home as well? No, I don't see hand raised.
Yes, I have Mirko. I have one.
Yeah, on you go.
Yeah, my question is related to the first one question. I remember that Tarski in his paper, What is Elementary Geometry, gave only the inner form of Pasch axioms, but he analyzed both its inner and outer form with Givant. I remember a paper with Givant. It was a letter and then a paper. And but I don't remember it is correct. Can you say more about the Givant-Tarski analysis of Pasch actions?
Yeah, there is a little bit more in that paper. That paper is actually a letter that Schwabhäuser wrote,
Yeah,
which then was published in the Bulletin of Symbolic Logic. And there you have also some special forms of it there, where there are these where they're similar to the existential parts of the where you don't have for every line, but just some line exists and so on. So yeah, there is a deeper analysis. Now, Tarski did not need anything beyond inner Pasch because in the Tarski-Givant paper, because at the time already his PhD student Gupta had shown how to prove outer Pasch with inner Pasch inside absolute geometry. And this was a tour de force. It's really very a major achievement. So we've shown that you can't get outer Pasch out of inner Pasch in ordered geometry. But if you add congruence, and if you have your statements of, if you have segment congruence, then you can prove it. It was done in 1965 by Gupta. So inner Pasch is enough there. And I mentioned it when I did in my constructive geometry talk, because I said absolute geometry can be axiomatized with quantifier-free axioms with just two operations. Segment intersection, so given 4 points, you give me the point of intersection of the two segments. And segment transport. So segment transport means that if I have a ray like this, and here I have a segment, then I can take this segment and transport it there. And that was possible. I mean, showing that this is possible worked because I used heavily Gupta's results. Because basically what that says is that in absolute geometry, you don't need the intersection on the extension of a segment. That just the intersection of two segments, which is what inner Pasch gives you, is enough. If you have this and segment transport, you're done. You can say anything you ever wanted to say.
thanks.
Okay, so if there's no other questions, I don't see them here. No more online. I'd like to first remind everybody that the next lecture from Professor Pambuccian is tomorrow from 9 to 11. And this said, I would like to thank Professor Pambuccian again for the lecture. And see you all tomorrow.